Section 4.5 is on linear approximations. I am going to first look at what we've been doing. We've been writing the equation of a tangent line by using this point slope formula. And we like to say we're looking at some point that's our derivative. We're looking at some point that's close to an A, and we get those two points closer and closer together by my definition of derivative. If you remember, we had some point, and then I would get the slope using the derivative. So this would be my f prime at some point A if I let x1 equal to A. So let's rewrite this. And what we're looking at, this is the f value or the y value at that A. This is my f prime at A. Okay, let me rewrite one more time. And this section is about getting an approximation for the y value. And we're going to call that a linear approximation. We're going to give this the designation of L, capital L, of x. And this is just going to be an approximation of that y value. So this f of x is going to be approximated using this f prime of A. And this is going to be a fairly close approximation as long as my x and my A that I choose are very close together. Alright, let's look at the problem that we have before us. I'm traveling down the road at my average speed is 60 miles an hour. So here's my average speed. And I'm counting the time in between mile markers, and it should take 60 seconds if I'm traveling 60 miles an hour. So if it takes me 62 seconds, then I'd like to know exactly how fast I was going, or if it takes me 57 seconds, they don't mean this. They meant x equals -3. My x is going to be how far above or below that 60 seconds that it takes to go between mile markers. And I don't want to use this formula every time, although it will give me that value that I'm looking for. I'm wanting to know what's my speed, my average speed in between any particular set of mile markers. That's what I'm really looking for. I'm going to use this linear approximation for that. So I need to know what s prime is. That's going to be -3600. And then I'm using the chain rule here, taking the derivative of the outside, leaving the inside alone, and subtracting 1 off of there. So I get something like 60 plus x quantity squared. Okay, that's all well and good. Now I need to use this linear approximation formula, and I'm wanting this A to be, if I'm traveling 60 miles an hour, I want the time in between mile markers to be exactly 60 seconds, because that's really what it should be. But it's not going to be. That x is going to vary. So that's going to be the point I'm going to revolve around, is this A equals 0, because at 60 seconds that would be identically 60 miles an hour. So that A would be 0 there, and then the x value is the number above or below that 0. So that's my reference point. So I'm going to need s prime 0, and this is going to be over 60 plus 0 quantity squared. This is going to be a -1. I'm also going to need s of 0, and that's going to be 3600 over 60 plus 0. This is going to be just, let's see, that's going to be a 60. I think I have everything I need. I found those. So my L of x, or my linear approximation f prime, that would be a -1 times x minus this 0 plus the 60. Rewriting, that would give me 60 minus x. So my linear approximation for this particular problem, my linear approximation to the average speed, says just take whatever it is and subtract it from 60. Okay, so let's choose I was traveling down the road, and let's say I counted the time in between mile markers to be 64 seconds in between mile markers. That would mean that my x is 4. And this would mean that my linear approximation to this would be I was traveling 56 miles per hour. That's because it took me a little more time than 60 seconds to get from one marker to the other. If, let's say, my speed were I counted the seconds in between mile markers, and let's say it was 54 seconds because I was going a little faster. That would mean that my x in this particular case would be my -6. And the linear approximation to this would be 60 minus a -6, which would let me know I was traveling 66 miles per hour. Alright, I think we've done it. Don't know that you would necessarily use this while you were driving down the road, but we can do it. Alright, we're supposed to do the linear approximation not using a calculator. We're going to use linear approximation to figure out what the value of the square root of 1.1 is. Because if I didn't have a calculator, this would be difficult. So this is one where it might come in handy, and before we had square root functions on our calculators, and yes, it wasn't that long ago, this was something that was very doable, and you could get a pretty good approximation. So for this particular case, we're going to choose our a to be 1. The reason they choose an a to be 1 is because I can calculate the square root of 1 very easily. So if I was looking for, say, the square root of, oh, I don't know, let's say 5, I would use x to be equal to 4, so that I could, because I know the square root of 4. Alright, here we go. What is f prime of x? That's going to be, drop your 1/2, x to the -1/2. This is going to look like 1 over 2 square root x. My a in this case is 1. So I need f prime at 1. It's going to be 1 over 2 times the square root of 1. I can get that pretty easy. That's 0.5. I'm also going to need f of 1. And the square root of 1 is 1. Right, so now I can play L of x equals f prime of a, that's 0.5 times x minus my a is 1 plus my f of a, that is a 1. So L of x is 0.5 x, that's a minus 0.5 plus 1, so that is plus 0.5. Alright, so let's see if we can find out what the value of this 0.1 is. So L of 1.1. Right, just chunking this in. If I crunch these values, I'm going to get 1.05. And I didn't have to take the square root of 1.1. But if I were to take the square root of 1.1 on my calculator says that this is about equal to 1.0488, and it goes on and on. So that's pretty darn close. I like that. Next up, they want me to use this same formula that I just got for my linear approximation of the square root of x near 1, is they want me to try to find linear approximation of 0.1. It's kind of further from 1 than I might like, but let's see what we get. 0.5 times 0.1 plus 0.5. And when I do this, I'm going to get 0.55. On my calculator, I get that, I'll just write it as f of 0.1 is more like 0.3162, which is kind of far off. So I don't really like this. Let's choose another a. I want to choose an a that I can easily take the square root of, but that's kind of close to 0.1. And we'll see what we can get. What about 9 over, and who would choose this unless you had done this before? Let's choose a to be 9 over 100, because that is 0.09, and 0.09 is kind of close to the 0.1. So let me get those numbers and see if I can come up with a new linear approximation where a is the 0.09. So f prime of 0.09 is going to be equal to 1 over 2 times the square root of 9 over 100. And that simplifies pretty good. I get 1 over 2 times 3 over 10. And this number is going to be, let me get this on my calculator. Alright, I just went ahead and got those values there. And now I'm going to plug into my linear approximation formula. L of x equals f prime of that value, that's 5/3, times x minus my new a, which is 9 over 100, plus f of a, which is 3 over 10. And they would like for me to do x equal to 0.1. I'm just going to call that 1 over 10. And then I'm going to work my fraction for you. Alright, so I worked out my fractions for you, and I got that my approximation is 0.3167. Here is what the calculator gave me. You can see it was really close. And before we had square root buttons on the calculator, I could still take the square root of 1.1 by using linear approximations. Really cool stuff. Alright. When I first started college, they just came out with calculators that had these trig functions on them, and it was a glorious thing for you to be able to push sine of some degree and have it come up with an answer instead of looking at tables in the back or doing these linear approximations. It was very nice. So here we go. We're going to figure out how we can get the sine and cosine of something without really having a calculator that might be able to do that, or without having tables of values, just looking at things from the unit circle perspective. Since I want to know the sine of 2.5, I go to something that's close to it that I actually know the answer of. And I know what the sine of 0 degrees is. The sine of 0 degrees, that's the y value, so that would be 0. I want to know the sine of 2.5, so I'm going to let my a be equal to 0 because I know that value. F prime of x is going to, oops, I was supposed to take the derivative of sine, so that's going to be cosine of x. I need to know f prime at 0, so cosine at 0 is going to be a 1. Then I need to know f at 0. F at 0 is, we discussed, equal to 0. Let's do our linear approximation. F prime at 0 degrees, x minus the 0 degrees, plus f of 0 degrees. So L of x is going to be 1 times x minus, I don't need to write that, plus a 0. So L of x is going to be equal to just plain x. Okay, I'm sure they mean that in radian form. So what's the linear approximation at 2.5 degrees? That means I need to put this in radians so I can get that value. So 2.5 degrees times pi over 180, just doing a radian degree conversion. And then this would be if you reduce pi over 72, degrees cancel, leaving me with about 0.04363 radians. Alright, let's punch it on the calculator. What is the sine of 2.5 degrees? The calculator says that this is about 0.04362. Oops, 2. Dang, that's close. That's awesome. In this, we're looking at differentials. We're not going to concern ourselves with the actual y value. We're going to concern ourselves with how far the y goes up in relationship to how much the x goes up or down. And if you'll notice that this is just change in y's over the change in x's, if I rewrite this, just saying that that slope is equal to that change in differential. Alright, I'm going to use that to approximate the change in y when x goes from, that means that the change in x in this case is 0.05. So I will get the change in y equals, I need f prime at a, so let me go get f prime out here this side. F prime of x is 9x to the 8th minus 2. And I need to know that f prime at that particular beginning value, so that I need f prime at that 1. So that's my beginning value, because I'm letting x be the 1.05 and I'm letting a be equal to the 1. So 9 times 1 to the 8th minus 2. This gives me a value of, I think about 7. Then what is, no, that's all I'm going to need. Okay, so this is just going to be 7 times 0.05. Really? Isn't that cool? There's the change in y. For that little change in x, I got a 0.35 change in y. That's pretty neat. Change in surface area of a spherical hot air balloon. Well, I guess I'm going to have to know the surface area of a balloon. So the B part, the surface area of a sphere is S equals 4 pi r squared. And I want to know the change in S when the radius, it goes from 4 meters to 3.9, so that means I want to know when it decreases by 0.1 meters. That lets me know that A is 4 and X is 3.9. I'm going to use this differential formula. I already have the delta R. Now I need the delta S equals, let me get that derivative of S. S prime with respect to R is 8 pi R. So I'm going to need S prime at 4. 8 pi times 4, so this is going to be 32 pi. Let's get our delta S. Delta S equals S prime at 4. I'm just going to go ahead and write that all out. S prime at 4 times delta X. This is going to be 32 pi times delta X was, or delta X, delta R, sorry. Delta R, negative 0.1 and this is going to give me, if I crunch it on the calculator, I'm going to get negative 10.05 meters squared. So if the radius goes down by 0.1 meters, the surface area goes down by 10 meters squared. Now that's when this hot air balloon, when that radius is near about 4. So it doesn't apply if I'm talking about it at 1 or at 10. Just formalizing our differential idea. Notice that this thing right here, there's my change in y, there's my f prime, and there is my dx. So that dx meaning that little change in x. So they want me to formally write out in this notation what this dy would look like. So what I'm going to do is I'm going to take the derivative of f. I'm going to need that. And this could be rewritten. I'm going to rewrite it over here, make it very clear what I've got. I've got cosine x quantity squared, so I'll need to use the chain rule. The chain rule says I need to take the derivative, drop that, so that would be 6, and I would leave the inside alone, times the derivative of the inside, and that would be a sine. Recognizing this is a double angle formula, you can make it look a little simpler. Not a big deal if you don't, but you can. So I'm going to say it's 1/2 times 6 sine of 2 theta, which then makes that 3 sine of 2 theta. If you happen to like the look of that better than this cosine times sine, that's fine. If you don't, that's okay too. So dy is going to equal 3 sine 2 theta. Oops, not theta. I meant to write x's in there. I wrote this in terms of thetas so that I wouldn't get confused with these x's, so now I put the thetas in there. Let me change those back to x's. Alright, I got my little mess up fixed there. Sorry about that. And then dx, just copying down what this differential says right here, just writing it down. And for a small change in y, that is what you would get. Alright, if you have any questions, see me at the Collaborate.